So I'm going to present scopes describe frames. So this is work on programming language engineering that I did when I was at postdoc at TU Delft a few years ago now, a couple of years ago. So what this is about? Well, the idea is that we want to have one specification for a language, and from this specification we want to derive all the tools, all the machinery that you have around a language. So you want not only a runtime, that means something to execute your program in that language, but you want a type checker or things to assist you when you write programs, an IDE, I mean a real one that can do name resolution, that can give you the type of the term you write, that can do syntax highlighting. And you may also want to write proof or about your language or formalizing stuff. So you want to be able to have some kind of specification of your language in a proof assistant. So what does this specification looks like? Well, usually it's two parts basically. You have three parts. You have the syntax on one at first, and from the syntax you then have two things. You have the static semantics. So how names behave in your program and how you can have types, and then you have the dynamic semantics. So dynamic semantics just tells you how your program executes and what is the result that is expected from your program. And when you formalize that part, well, the bindings have a really predominant part, because in particular when you start doing proof and when you start doing type-channelized proof, you see that all the complexity is usually in how names behave and how you represent them. And changing the representation can change the proof and make it simpler or much harder. It's really it's a really critical part of the design of your language. So how do you deal with names in both the static and the dynamic world? Well, when you have lexical scoping, you just have variables that define, and well, when you reason with that, you can work with on the static world. You can work with context, so you store the current values of your variables and their type, and you make that evolve when you go through the program. When you formalize the dynamic of your program, you can also use like substitutions. You can keep the environments that you had. You can use other formalism like Dublin indices or higher order abstract syntax that basically embed your language into the meta language that you're using to formalizing it. Well, things are a bit more low level when you talk about mutable variables, but the idea is that you also have to maintain a state that maps basically your names to your types or to your values. And same thing when you have objects, it's just that the structure that represents, that you associate to names can be nested basically. So you can have environments, well, you can have names mapping to environments that are themselves mappings. So the idea is that all of this is not really unified, and we wanted to come up with something that better represents all these different paradigms. And that's what we came with scope graph. So scope graph is an idea of how we can represent the name binding structure of a program with the scope graph language being independent of the language itself. So it's like a type system that you could apply to several languages, and it's a common representation which you can work with. I mean, once you have this graph representation of a program, you can do resolution. So you can know from one variable or one occurrence of a variable where does it resolve, just by basically building a path in that graph. So how does that work? Well, so if we take a very simple program that has two definitions, x and y, so I just annotate the different occurrences of, so this is the real program, this is the annotated program where I can say x1 resolved to x2 because these are two occurrences of x, one is the definition and one is the use. So it's not two different variables. So in this case, we know that, yeah, well, x2 resolved to x1 because everything is in the same scope. We have defined two values, and that's it. But how do we represent that? Well, in scope graph, we just have one scope that englobes these two definitions of the program, and we just say that, well, there is a definition x1, So it's an arrow pointing to that one, and there's a definition y1. And then we have a reference also in that scope. And if we try to resolve x in that scope, where we just build a path from x to its scope, so from the reference to the scope itself, and then from the scope we start looking for definition, and we find one. So that's the very basic case. But even here we can see that we can have some weirdness. So you can have, for example, ambiguous definition. So how do you know that you have ambiguous resolution? Well, you have basically two paths that have the exact same form that are resolving the same variables. So that's how you would see an ambiguous resolution. Or some cases are you want to exclude them. In some cases, it's not really obvious what you want to do. So this syntax, for example, is allowed in OCaml, and it's okay as long as you bind the exact same variable in all patterns. So now, okay, everything was in the same scope, but we can have nested scopes. So we don't know that we don't have just one big bag of definition, but we have nested definition. And so for example, in this case, we have a first main scope which defines x and z, and then we have a nested scope which is inside it, and that defines a y and reference an x and a y. So we know that the reference that belong to S1 can basically see the reference that are in S0, but not the other way around. So, and that's reflected in the graph because, well, you can build path from everything that's in S1 to things in S1. You can build path from something that's in S1 to S0 by just using this parent edge here between scopes. So you can just follow the graph, and once again, you can resolve. And you have a second rule basically on top of the just reference definition. So this is the reference rule, this is the parent rule, and this is the definition. And now we can define that the word form path is just a reference, then a sequence of parents, and a definition. So now how do we have shadowing? So shadowing is that when we can more or less see multiple definition of a variable, but we don't know how to resolve, or we have to tell how to resolve. Because, for example, here we have this variable x2, which is in the scope S2. So you can see that from this x, from the reference, we can see both the definition that is in scope S1 and the reference that's in scope S0. And to tell that, well, we have two paths. We have one path that uses twice the parent edge, and we have one path that uses it only once. So we just have rules to compare paths and to say, well, one path is better than another, and that's how we disambiguate this. So we can deal also with imports. So imports will be just, so these are OCaml modules, more or less. And an import is just a name referencing another set of definition. And in that case, you have like several resolutions, because how do you resolve the z here, the z2 to the z1 that is in the definition of module A? Well, here again we introduce two more arrows that are the import and the associate. So the associated scope means that you can associate a scope to a variable definition. So here the definition A1 has associated scope SA that contains the definition of Z. And the idea is that from X, starting from Z, we will find A. So from Z, we go to its surrounding scope, which is SB, and in SB, we see that we have an A. So from A, we can start the resolution of A. We resolve A to its actual definition, A1, then we find the scope corresponding to A, and we can eventually resolve Z in that scope that we found using A. And that gives us our last rule. So now you can basically tune your language, so not only by the way you generate graph, but by the way you compare paths, for example, so or by the kind of path you allow. So for example, here we have two resolutions for Z. We have a resolution where that uses the import, and you have a resolution that just go to the lexical surrounding scope. And it's not clear, basically, when you have language, which one you want to prefer. And you would just say that by, well, saying, okay, if I want to prefer imports than parents, then I just declare that the import arrow is basically weaker than the parent arrow. And it can be the other way around. You can use transitive imports by just putting a star on the number of iterations. Well, by allowing as many iterations of the parent rule that you want. You can say that, well, once you use an import, you cannot go to the parent anymore. So going from A to then the parent to the definition D3 wouldn't be allowed, etc. So yeah, so this is the example of the transitive imports that use, well, first the resolution of import B to the module A, to the import B to the module B that imports A, and that gives us the definition. So it's basically so when you have language, basically what you need to do is provide a way to generate the graph from every program, and then one set of rules for this language. So basically it's just one regular expression or a set of regular expression, and a way to some kind of weight on the different arrows to see how you resolve shadowing. So yeah, so these are two examples. For example, so here we have the transitive import version and the non-transitive import, which allows at most one import. So that's the four rules of our language, and it allows us to represent quite a large number of patterns that we find in usual programming language. And we can formalize that. So using the real version of this rule, these are the resolution rule that says that, well, how does a particular occurrence of a variable resolve to a definition? Well, you just have to see what are the visible declaration, and then do the, yeah. So these are this is the parent edge, this is the import edge, these are the transitive closure of repeating, and then you have the comparison of the path. So this is the check that the path has the correct shape, so satisfy the regular expression. This is the path comparison to disambiguate, and then it gives you the hopefully only one resolution. I mean, a program is correct if every occurrence has only one, has exactly one associated definition. So that's for the static part. And then, using that, we wanted to do type soundness proof. So that representation is not really easy to work with if you have just like rewriting rules, for example, to specify your semantics. So the idea that we had is that, well, this code, basically, we can populate them with variables. And that's what we call a frame. So if we take the first program and we evaluate it in order, you just say, okay, well, I have so here are the scope are nested, but basically you have your definition of X that you can, well, you see its definition, you resolve X, and its value is 31, and then you have another, you go to the next line, and then you open the new scope, and you go to Y, and then in to resolve the value of Y, you need to resolve X, and now you can basically use the graph representation, so the static scope graph that you had. It's fully resolved, so you know that X, you just go to the parent and you find the definition, and that's basically what you can do at the same time in your dynamic structure. So the idea is that the view that you will have from your dynamic structure is exactly the view that you will have from your scope graph. So the dynamic doesn't represent the entire scope graph because your program is not fully executed at that time, but everything that you can view from the static scope that you are in somehow is also accessible in the dynamic part. That's what the invariant that you want to maintain. So here we have this Y, and we want to find this value. We want to find this value by resolving the X. We follow the exact same path than that is given basically by the scope graph, and we get its value. So if we take something a bit more complicated, so here we have a recursive function, which is usual example. So we arrive at the top at the definition. Well, we have one scope that declares a variable, which is fac, and its value is a function. So it's the closure that is the body of the function, and then you want to evaluate that. So you go to the second scope here, and sorry, I lost. Yeah, okay, we go to the second scope and we need to resolve fac. So fac is already existing in this scope. It's trivial. And then we open the definition of the function and we get the new scope, which is the scope of the body of the function. And in that new scope, well, we have 3 occurrences of n that are the 3 here. So the n, and the n, and we have 1 occurrences of the function name itself of fac. And same here. So what we do is that, well, the names are resolved locally and the fac is just resolved in the parent scope because the definition actually belongs to the parent scope. So this is the parent scope and this is the nested scope inside, but this definition is actually in this scope, as you can see it here. And same thing. So you constantly have a view that is, well, from where you are in the dynamic world or in the program, you can see the same thing in the frames that you were able to see in the scope. And that evolves. So you have a first frame where, okay, you plug the value 2 inside n because that's the initial value for your call, and then when you do your recursive call, you just look up for the function, and then you create a new scope, a new frame, sorry. So the view from this frame is still the same because this part is basically invisible to it, and the structure is maintained. And that evolves continuously, and then we create a new one where n is equal to 0, and there we don't have to resolve fac, and we're done, basically. So yes, these frames are basically a dynamic evolution of the scope where we have to maintain this invariance. So we have the same thing here with a class where you just have, well, one of the elements referencing a new frame that contains 2 values, and you have, again, this parallelism between the scopes and the frame. So we have the static definition, we have the dynamic definition, and using that, well, we can have this famous property of well-bound frame and well-typed frame. So well-bound frame is what I was talking about, is that, well, the view that you have on one side is exactly the view that you have from the other side. So every definition in your current scope has to be instantiated with the value, and every basically edge that can lead you outside of your current frame has to be populated and has to point to something that is also instantiated. And the well-typed property is, well, the same thing with type. So everything that you see and has a value has to have a value of the correct type from the scope point of view. For the scope, you only have to type the definitions of the different variables, and from the frame point of view, you just have to check the type of the value. And by maintaining these 2 invariants, you can just have a whole set of language-independent lemmas that basically brings helps you to lift your scope generation and your frame generation. You just have to prove that these 2 invariants are maintained, and then you can derive a type soundness proof. So you go from basically a small step proof to the entire program level. So yeah, so these are the 2 invariants, and by having the group frame, you just maintain the invariant, and if every frame is well-bound and well-tied, then and if that is maintained, then your language is type sound. So yeah, so you have the part that is language independent. So the language of scope is independent. The language of frame is independent, and then you have the part of language independent lemmas. But of course, you have some specific some parts that are specific of your language that are choice that you made in the design of your language, and that will require you to complete. Basically, you got a proof, but with holes inside. And depending on your language definition, you will be able to complete the holes or not. The other idea is that, well, you can also use this invariant to do garbage collection. So what I was saying is that, well, at some point you have a view from your frame that corresponds to the view that you have from the graph, and basically everything that is not accessible from your current frame can be more or less can be simply removed. So that's also give you a high level idea of what your garbage collector would look like, for example. So yeah, that's basically the frame referencing outside of the frame referencing inside A. Then B is not referenced anymore in your current frame view, and you can get rid of it safely, and that gives you a proof that your language is correct. So that's more or less it. So that's the idea. So you have seen that we can have this new name binding specification that by just requiring a few lemma to complete, that will really depend on your implementation choice, to derive, well, a type soundness proof and a garbage collection soundness proof. That's it.